Boom. Hello and welcome back to Calculus 3. Today we have a review for the upcoming exam that you want so much. Hopefully you are working on your quizzes. Today quiz 2 expires at midnight, so hopefully you are working on that stuff. Quiz 3 tomorrow, 6 a.m. Don't miss it, right? The quizzes will be opening and closing every day, starting 6 a.m., closing at midnight, well, minute before midnight. And you guys will have 7 of those. Apparently you need 70 or more, right? Okay. Because I know there was some requests to be 80. We can also drop the highest grade. Anyone? No? All right, fine. It works like a charm, by the way. Anyway. So we are going to have exam on chapter 11. Oh, by the way, the graph the function and you get the heart and, right, do all of that. All right, so chapter 11. I would say about 10 problems. Could be less if I have a lot of A-B parts, and could be more if, one of the questions just say, write the formula for dot product. I mean, if that's problem number 4, right, in that case, we better have more than 10 questions. So 100 points, and then you have your quizzes. About hour and 20 minutes in class, and we'll do that at the beginning of the class, and then follow with the 12.1 lecture right after that. You voted for next class, so that's technically it. And just make sure nothing crazy happens. I told you the day 1. If you choose to have an exam and you vote on a date, not even a handwritten note from God will excuse you from that one, because we are not on good terms. What else? So, topics. Oh yes, we will have some of you signed up for honors option. You guys will have extra questions. Generally, I have 2 questions that are extra on the exam, which are all proofs, and 3 to 4 on the final, but final is 2 hours. So there will be proofs. You guys also have extra lab and 1 more project question and so on. So there's more stuff for honors. Yes?
So just to confirm, is that we don't have to use proofs for every answer, but we just have questions that involve...
You have the same exam like everyone else, and then you have 2 questions that are proofs. Yeah, that's that. So now, what is on chapter 11? So technically all problems and all sections that we covered are the part of the exam. And also, you guys will... so you might have some of the calculation questions, and some of those will state the formula and so on. So maybe I should make it number 4, because I already said it's going to be number 4, right? State the dot product formula, state a cross product formula, state the whatever limit of vector valued function and stuff like that. So that could be a question that just asks you to state the formulas that you might use. State the way to find the angle between 2 vectors, right? And you know to use the arc cosine dot product divided by the multiplication of amplitudes. So there are multiple possibilities for you to write that kind of stuff. Topics. So we have vectors, 2D and 3D. I know that you can deal with any n-dimensional vector, but we are only focusing on these. We have the dot and cross products. and their application, right? So what we have, the dot product application would be work, and then the torque for cross product, and then you have perpendicular, when you cross two lines, you get the perpendicular line. So all of that kind of stuff. It's not nothing special. Finally, we have lines and curves in space. And we are talking about straight line with the formula that you must know. That could also be on one of those theoretical questions. State the formula for the line, and then you write the parametric set, or you write it in terms of vector valued function. So for lines and curves, need to know all of those things. You don't have to memorize 5,000 shapes of any lines that are in, the formula for slinky or something like. No, none of that stuff. You must know the formula for the line. The x0 plus at, y0 plus bt, and z0 plus ct. You better know that one, because otherwise you're just doomed. Helix, yeah, why not, right? Because just cosine, sine, and then whatever else over there, t squared or something, depending on how fast you want it to go up. So you have just those basic shapes. There's no reason to memorize everything, especially if you have software to come up with those things when you need them. Vector valued functions. Meaning understanding that vector R is the set of parametric functions, and it will actually trace the function through space, right, as you go around. Then we have the calculus of vector valued functions, which are going to be limits, derivatives, and integrals. We know you do that term-wise, right, each component individually, so that should not be any issue for you. And if I put a problem where I say calculate, acceleration function given the position function, and you don't know that you have to take two derivatives, well, I'm sorry, where's your Calc 1, right? So you must know, you know your own name, you know how to tie your shoes, maybe, right? You should also know that the acceleration is the second derivative of position function. And your R of t is a position function. So welcome to Calc 3. Also, integration goes the other way, right? So calculus of vector valued functions. And that's going to include application, right? So it could be a vanilla question. Here's your R, find the limit as t goes to blah, right? Okay. Or it could say, here's the velocity function, what is the position function? Okay, velocity function, vector valued function, velocity function, so I have to integrate to get my R position. Oh, there's that plus c. Initial point is given, figure out the constant, right? So these are the things that are Calc 1 repeated in 3D. So instead of working with one function, you have to work with the x component, y component, and z component functions. Which brings us to motion in space. This section is, and this is where the trade-off happens. So as I said, you are Calculus 3 students, and if you don't know that the velocity is the first derivative of position and acceleration is the second derivative of position, and so on, and I'd be very upset if you don't know that. For 1.7 motion in space, these are all physics formulas. So I'm really not inclined, even though you kind of should know it, it's like been around for 500 years. But again, that section is purely physics. and it's a very low probability that the problem from there will show up on a test, and if it does, I'm also inclined to leave some physics formulas scattered around the problem, right? So you might stumble upon them. You are supposed to know all of these formulas by heart when you take physics course, and if you don't know them, well, that's your deficiency, not mine. And you can just use the Calculus 3 concept of the vector valued function to just wrap all of those formulas into single vector. So in that, when we did 1.7, we covered all of that. Obviously, you can go back and check the video. If you took physics, kinematics, you shouldn't have learned anything new other than, hey, I can put this in a single vector. Haha. And walk away. Technically, that's it. Lengths of curves, definitely. And we have three, right? You have the Calc2 one, which you still have to know, which is the square root of 1 plus derivative squared, right? And then now you have two new ones. You have the 2D and 3D version of the parametric form, which you must know, and the polar form, which is only for 2D. So those are the new ones. And again, you know there's no formula sheet or anything like that, so you just have to know Calc 3. Calculations are all Calc 1. That was a big argument at one point. You know, what do you mean no formulas in Calc 3? So what are you learning in Calc 3 then? If I give you the formula for a parametric set, then length of the curve in parametric form, right? So I just reduced Calculus 3 question to a Calc 1 question. Can you integrate? Right? That's Calc 1 question. Can you integrate? So you have to understand that you learning formulas and getting these concepts the way they work, that's Calc 3. Mechanics of solving the problem, i.e., do you know how to differentiate and integrate, that's all Calc 1. So there are not going to be formulas on any of the exams in Calc 3, and that's the course standard, so that's for every section. It's not just, oh, I'm mean and evil. It's just, that's what it is. So you have to understand that that's the only thing that is Calc 3, those formulas and concepts that you need to learn. Mechanics, what's the derivative of sine 2x? Right? 2. Cosine 2x. Yeah, I know it. Good. And then finally, we have curvature. Hope that's not that derivative, right? Oh yeah, now I made a mental note already. So curvature plus normal. Normal vector. Again, acceleration and stuff like that, that's all, again, physics. And if any of the physics formulas are necessary for any of the problems, I tend to include them, but I expect you to know 100% of Calculus 3.
Are you going to give us a mean normal vector that we're going to have to find for like the mean vector to get both curvature and normal?
You mean, oh,
ones that like
the ones that's going to go for 7 pages?
Yeah.
Maybe,
because if you don't put that on, then I might as well not even take the exam, because that's the whole purpose of it. Come on, right?
So he's rooting for the mean question that he will be able to solve. Yeah, Ryan currently doesn't like you.
5 average is better than I ever had, so.
Okay. And when you look at this list, does any of these scream unit tangent vector? No. But do you need to know it? Hell yeah, because this is not going to be there. Also, unit tangent vector is going to give you the slope of those tangent lines that are tangent lines here. right? So you have to know unit tangent vector. Now for honors, we have the proofs. And for the proofs, we said those vector laws that you have, the vector properties. There were like 1,700 of them on that one page. I will give you the property and I will say prove this property, and hopefully you guys will do it in 2D or MD, whatever. So we have those vector properties. We definitely have the arc length derivation. So going from the basic into parametric, going from parametric into the derivation for projection. I outlined in class the full proof in the book. If you have any issues, stop by, obviously. Lines and curves in space, I don't think we had anything there. Oh yes, linear line derivation for the formula. Linear line formula derivation. And the limits and the derivatives of vector valued functions, you know, the limits would be epsilon deltas component wise, and then derivatives would be the difference quotient formula component wise.
Curvature of a straight line.
Oh yes, I said, yeah, I said I might, yeah, curvature of the straight line. Curvature of the straight line is 0. I know there was one more, I just can't remember it. Oh yes, we used the arc length to prove the circumference of the circle. Arc length to prove C equals 2 pi r. That's it. I hope you're not disappointed if you're taking honors section. So some of these are proofs, some of these are derivations, meaning going from one formula, deriving another. And that's that. Now, before you ask any questions in class, I'm gonna make this fun line over here. Look at that. See you next week. Let's quickly talk about the flow of the Calculus 3 so far. So sure, we have vectors and all of that stuff, but I want to start first with a vector u that could be 2D, or it could be 3D, having 3 components. And then we can upgrade the vector into a vector valued function r of t, which will be, again, let's do the 3D case, f of t, g of t, and h of t. And then you can take the derivative of r of t to get the velocity of t, which is simply f prime of t, g prime of t, and h prime of t. Is it wrong that I'm actually rooting for this to start erasing things and crashing? I just can't. Like, anyway, the second derivative of t is going to be the acceleration. Oh, these are acceleration vectors. And that's going to be f double prime of t, g double prime of t, and h double prime of t. So we have those. If you go from position function through velocity through acceleration, taking derivatives, clearly backwards it's going to be integrals. Now this vector r will give you r prime, and then r prime will eventually give you t hat, which is r prime of t divided by the magnitude of r prime of t. And this is one of the very important formulas. Let's say you have a curve in space of some kind and you want to find the tangent line over here. You know that any kind of a line is going to be r of t is equal to vt plus r0, right? Well, this vt over here is actually your t hat. If you want to find the tangent line to a curve. So t hat is important. Gives us the direction, the 3D slope, let's say, to find the line. I was considering erasing this, but then I added, right? And then from t, which is given as that, you can go and get the normal vector in terms of t, which is t prime divided by the magnitude of t prime. Can anyone tell me the formula for curvature? Very good. What happened? T prime? Okay. Good. So these are the equations that obviously there are arc length equations and all of that stuff, but I would say that this is the core. You have the arc lengths ones. So Calc2, a to b, square root of 1 plus f prime squared of t dt. Or no, it was x. It's a Calc2 one. And now the Calc3, a to b, square root of, and now you have the dx dt squared plus dy dt squared dt. Now honors section will do the proof from one to another, I mean derivation. And another one for this one is alpha and beta. It's a polar coordinates one. Square root of f of theta plus f of theta squared plus f prime of theta squared d theta. Need to know all three. Especially the first one, because that's Calc 2, you should know, because you're sitting in Calc 3 now. So that's the one you You did well last semester. Here in blood. Know all formulas and definitions, right, as per up there. What else did I miss? I missed something. Oh yeah, the cross product, the dot product formulas, that's all there. I put them in here, but I didn't include anything in terms of computing vectors, adding, subtracting vectors. IJK notation, obviously. Yes?
You said VT, T hat is the same as VT, is that, so VT together? What did you mean by that?
No, just vector V. And then you are multiplying this by T plus R0 to give you the... Because T hat has a length of 1 and it carries the direction, the tangential direction. It's called the unit tangent vector, right? Yeah. So it's called a unit because the length is 1, and it's called a tangent because it's the tangent vector, right? So you have those two concepts in the name to help you. You see that when you use that, you understand that it's just a 3D slope, which way the line would angle, right? And then you have times t, so technically this is mx plus t, right? So your slope, and you know the slope of the tangent line should come from the derivative, right? Yeah. Good. Is there anything else? I don't think there's any. I hope you're not disappointed. Maybe I can come up with more stuff, but that's it. You want power series? Great. I just heard power series. So we can, let's add geometric series, integral test. I'm just scanning the classroom at this point. And alternating, that's it. Okay, that's fine. We'll include more for next time.
It's just have one, what was that one you said?
I mean, I prefer ratio myself, but...
Just the integral test.
Yeah, the integral test, because it takes 2 pages to solve. Exactly.
Simple addition problems.
Simple addition problems. 13 plus 9.
2 plus 1.
I did that once on the quiz long time ago, just to see the test taking skills. This is my first year teaching at RV, and I put I think it was a pre-calc 1 class. I put the Calculus 1 questions on the test, on the quiz. It was just 3 Calculus 1 questions on the first page, and on the back page I put 1 plus 1 equals.
I can see
Vast majority did not turn even. They tested, what the hell is this?
I can see we're gonna get our exam. It's gonna be those the 60-second multiplication sheets that they used to do in elementary school. You have what? I think it was like you had like 100-something problems or whatever to do in like a minute, and it was just all multiplication stuff.
Man, those are the days.
Those are the days?
That was fun.
All right. Do you have any questions, concerns before I shut down this review? Is the heart still there? Yeah.
How much will parametric equations convert into?
1 problem. Because it's not crucial. I mean, every time you write R, you are writing the set of 2 or 3 parametric equations. But it's not conversion from the Cartesian equation. So you can have maximum of 1 question to convert right now, and I'm not, freaking out about that, because in coming chapters parametrization is the core for survival. So you will have to get your parametrization straight later if you don't have it by now. Any other questions, concerns? Just questions, don't worry about concerns. I understand concerns are there. Just questions. Let's limit on that.
example of converting it? No one else has anything.
Sure, we'll do the example. Got so quiet over here. All that time. All right, so the question on, say, what convert to parametric set. Y squared equals to I'm going to sin x. Square root of x squared minus 3. Everything plus x. Whatever. What should I do? Anyone?
I mean, I just did some substitution. I substituted x squared minus 3 for t.
Okay.
Yeah, nothing too special.
So x squared minus 3 equals to t. So what would that give us?
Y squared equals...
Well, let's first solve this, right, for x. So x squared is equal to t plus 3. And then x equals to t plus 3. Is there a plus and minus in front? When you square root both sides? So, what should we do about that? Assume it's positive. That will help. So, can it be negative at all?
No.
Why not?
Because of y squared.
But it actually can. That's the problem. Because if you look at this over here, right? This term is always positive. And then if x is negative, so there have to be some conditions under which we can assume. So we'll deal with that. Let's, now that we have this, we can replace, now we have y squared is equal to square root of t plus square root of t plus 3. And if you square root both sides, now again y equals square root of t plus square root of t plus 3. Yay. Oh, plus and minus 2 in front. So these are the issues that, you know, we get with a parametric set. So I don't know, not too happy with the parametric set between this one and this one. Let's try something else. Did you consider y squared equals t? Would that help?
So it was wrong.
I asked if you help. I didn't say that's the way. Now that would mean that that if that is equal to t, then the other side, x squared minus 3 plus x, is also t for this. And now you have to solve somehow for x. And in this one, which is not going to be easy at all. It can be done, but you do is you square both sides. That's going to free this, and then it's going to give you minus 2 times x, another square root of x squared minus 3, and then plus x squared equals t squared. So as you can see, it actually is making it a little bit worse, but then when you square it one more time, it will actually get rid of the square root, and then try to solve it. So no, it's not going to give us nice parametrization there either. So this way over here is good way, but you have to come up with the conditions for positive and negative. Right, and then you can say, okay, if I use positive now, and so on. And the positive is that the sum has to be positive, because y squared is always positive, so bigger than 0. So this goes if, and you keep it right, if the square root of x squared minus 3 plus x is larger or equal than 0. So that's the condition. Now you can solve that by moving x to the other side, squaring both sides, and you can come up with a condition under which that becomes positive, and then you actually have your parametric set for those values. So yeah, converting to parametric equations when you have whatever kind of equation is not an easy task at all. Maybe let me just go find a problem in a textbook that you guys can consider, dare I say, enjoy. Before that, let's see another one of these guys before I go there. So how about x squared over 16 minus y squared over 9 is equal to 1? Any ideas of what we should do there? Oh, sorry, plus, not minus. In the middle, plus, 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 plus. Yeah. Wow. Sorry. It changes completely the concept and everything. So what is the parametric set here? What is this? Ellipse. Good. So what is the parametric set?
X equals 4 cosine t and y equals 3 sine t.
X equals 4 cosine t, y equals 3 sine t. Nice. When these are the same, it's a circle. When they are not the same, it's an ellipse. And that's the end of the story. So it's one of these ellipses. This is 4, and this is 3. Good.
That's just something you have to recognize and memorize.
Because the set, the circle is a special case of an ellipse. So ellipse is the main shape. Just like rectangle is a main shape, and then if all sides of the rectangle are the same, it's a square. Special case. So if you have an ellipse, it is going to be x equals a cosine t and y equals b sine t, and in case that these two guys end up being the same as r, then we have circle. So if the numbers are the same, it's a circle, and that's the radius of the circle, which goes on the other side. You can also, convert this. If you have, just to clarify this, if you have x squared over 9 plus y squared over 9 equals to 1, this is a circle of radius 3 written as equation of an ellipse. But again, circle is a special ellipse, so they have to have the same equation. Now you see a common denominator there, so you can multiply everywhere by 9, and immediately you get x squared plus y squared equals to 9. So circle with radius 3. So we know that part. Now as soon as I replace one of these 9s with any other number than 9, it immediately becomes an ellipse. So as you can see, ellipse has the major radius, in this case a, and then the minor radius b, and when those two are the same, you actually get the circle. Good. Many other questions, concerns? Just crickets. Good. I mean, I'm happy. You know everything, which is great. So exam is next class. Now we're going to do the lab and just leave. Yep. Bye.